Now that the engine configuration area is set up, we now need to go about getting the ECU into sync with the triggers. This is either done as a generic crank and cam setup or using one of the predefined crank and cam setups of triggers that we support. First of all, these can be seen in the crank and cam type, as explained in the previous video, to assign the selection to suit your engine type. Now, what we need to do, I'm actually going to go along the assumption of I actually don't know what the trigger is on this. So what I'm going to do is actually have a look at some sync logs to see what the data shows and then set up the crank and cam to suit. So what I do know is that I have got the crank sensor wired into AN06. So AN1 to 8 on the S6 are frequency inputs, and on the S8 and S12 AN1 through to 16 are all frequency based, so they can handle a trigger wheel from a crank or a cam. So this is an S6 and we've actually got this basically wired, so the crank sensor is on 5 and the cam sensor is on 6. But we can just double check that. Now what I'm going to do is I'm actually going to program those changes in. So the cam phase is set to ANO6 and ANO5 is there. Now the ECU now comes online, as we can see, but what's important is now to ensure the engine doesn't try to start. So under starting and under engine enable, there's an option here for engine enable throttle position. So what I'm going to do is I'm actually going to set that as 0, and you can see the engine enable state over here on the right hand side has gone to TPS start, and fuel cut severity and ignition cut is at 100%, so the engine won't try to start. Now what we can do is actually have a look to see what is going on with our trigger pattern. Now before we actually get the car cranking over and the engine turning, what it might be worth looking at is looking at the type of sensor that you've got. So this one has got Hall effect sensors. So what I need to do is I need to go into sensors, look at my crank and cam setup and ensure they're right. So Hall effects most of the time generally needs a pull-up assigned to it, so that you would use and set it as a thermistor type. If you were using a bipolar type of sensor, VR sensor, then you would select 5 volt bipolar. If it's the Hall effect sensor doesn't need a pull-up, then you would just select 5 volts. Then what you've got is you've got input filter, which we don't want. I'd really recommend that's never used. And then we've got the high and low trigger threshold on the voltage for in cranking and when the engine is running. So these are important to look at, and we'll come back to those after we've got some data from the car on cranking. So what I'm going to do now is actually crank the engine over and have a look at the log from the trigger settings. So as you can see, the sync state didn't actually change to, from stop. So what that means is basically it's not actually seeing a pattern of any sort on the crank sensor input. So what we need to do is now go to pin assignments and actually have a look at these inputs in a raw state. So we want to look at 5 and 6. What we can do here, we can right click on these, make these normal, and then change these type to a trace. Frequency 50 Hertz. Okay, so we're going to do the same again and have a look to see what we've got. Okay, so AN06, if we just pause that, we can see that there's one tooth that's coming, probably looks like every rotation, and then we've got lots of teeth coming on the AN06. So actually the AN06 looks to be the crank sensor and the cam sensor. So what we're going to do, we're going to change these round. It's very simple. I'm going to program that, bring it back online. Now what we should do, when we see it, we should now see it says turn in the top right hand corner up here. And what that means is it means the ECU is seeing some sort of pattern coming off the sensor. It's not keyed onto it, but basically we can now look at it in the sync log. So if we go to device at the top and then view sync log, under here now we can actually see the wave pattern from the sensor. So it's purple at the moment because it's basically not locked onto it at all. So what we're looking at that's important is we're looking to see the voltage threshold which is jumping between. So we can see here that it doesn't actually go all the way down to 0. So what we're going to think is a low trigger threshold that would probably be wise would be something around about 1.5 volts, and then the high trigger threshold something around 3.754 volts. Now, one thing to bear in mind, if you're using an AN01 to 04 on an S6, these thresholds can be adjustable. if you're using AN05 to AN08, the unipolar inputs, these have fixed thresholds which are 1.25 and 3.75. So these are the best types of inputs to use for a Hall effect sensor. So we don't actually need to change anything in terms of the thresholds because they're already hard set, and if we were to change them in the sensor setup it makes no difference. Now on a Hall effect sensor it can be difficult to see which edge is best to trigger off. On a VR sensor, a good tip is that look at the edge, which is basically the delta is travelling faster. So if the edge is falling faster than rising, then the trigger would be a falling edge. And the same would go for that. Now on this, basically because it's actually a Hall effect sensor, it looks like this is probably going to be more a rising edge. So I'm going to go back in to our crank sensor. There's no point changing these. As I said, these make no difference. If I was to put that at 0, it would still pick up the trigger because it's hard coded. As you can see, it still sees turn. Put that back. And then the trigger edge, I've actually got it on falling. It doesn't. I can leave it on that for the minute because what we're going to have to do is after this we're going to actually have to get a timing light and verify that our pattern is fitting. The rising and the falling is identical. Whichever edge is cleanest is the one to use for your edge type. So we'll leave it at falling for now, and the reference angle adder we'll leave that at 0. So we know now that it's seeing the cam and crank successfully because when you look in the sync log you can see the little red lines here, which basically means that the FPGA is picking up these trigger points. So that's a really good start. What we need to do now is we need to get that to go green. So what we need to look at is a type of trigger. Now it's very easy to look at a trigger and actually count the wheel, but we can actually do this in the sync log. So we're going to do that right now. Here we can actually count the amount of teeth the ECU is seeing, and then what we can do is look at the trigger wheel in our hand to actually verify that what we're seeing matches what the ECU has. And the point of that is actually because where you can see there's teeth on the cam sensor there, we need to know if those are actually two teeth part of one rotation or actually just one tooth part of one rotation. Now I know this trigger wheel because I've actually looked at it externally, and this actually has one tooth on the cam wheel. Okay, so we can actually then see that between each one of these tooth, because the cam is going to turn twice as the times the speed of the crank, we then need to know how many teeth we've got across between these two cam teeth, and actually from that point we can work out the crank teeth. So what we've actually got is we're going to say zoom in, and we can get the two cam teeth here and then count between. Now it's on the falling edge, so every time one of those teeth falls we can use that as a point. So I'm going to go through these and count. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so basically we've actually got 24 teeth between the two cam pulses. So what that actually is going to mean is it's got a 12 plus 1 trigger wheel, and this is actually classed as a keyed by single cam. So what we're going to do now is actually go back to our engine configuration area. Number of crank teeth, so 12 is correct. Number of crank tooth gap definitions will be 12 because there's going to be 12 teeth and 12 gaps. Then the crank reference tooth angle. Now this is the angle of which the engine is going to be synced to match the ECU in terms of timing. Now this will need to be done with a timing light unless you actually know the setup of the tooth wheel. Some manufacturers of the trigger wheels will actually give that, or you can find it in the documentation for the engine. If not, what you need to do is need to get a timing light on cylinder number 1 and then go to the output test mode and turn on the ignition timing mode, and what that would do is when that's enabled you can fix it at a set angle, and then when the engine's cranking and it's got sync, it will basically you can match the ignition timing of the ECU to the engine. So we're going to keep going through these. Now the crank tooth gap whips, these need to always equal 360. So on this we've actually got 12 equally spaced teeth, so we do 360 divided by 12 equals 30. Now if you had a wheel that had, say, a missing tooth, what you would actually do is you'd actually have one of the points, the next one most likely, at double, because that actually would simulate a missing tooth. Okay, but you need to make sure that they all add up to 360. We're going to do that. So for this type we've got the 30. Now the minimum and maximum gap whips, good thing to do with this, a good setup, you can go copy the gap whips, paste them into the minimum, and then do math multiply 0.7. It's a good starting point. You can go less if you want to to be even more like open, like 0.5, but generally 0.7 is a good one for me. And then the maximum width, we can highlight those, paste, and then SA math multiply 1.3, and those values then should be good enough in order to have some gap widths. After we've done that, the gap repeats, there is no gap repeats on this, so you can all be set as just 1. And then from this, we know that this is a type of cam and crank type as a keyed by single cam, because basically the cam is what is keying the ECU to know where the TDC is. So if we go to cam and crank type, change it from single gap to keyed by single cam. If it had a missing gap, like a 60-2 or 36-1, it would be single gap, single cam. I'll come back to that in a minute. And then under here, what we've got then is we've got the Omit cam detection validation. So basically, we'd only need the cam to turn once in order to validate it. It allows it to start faster. If you've got an intake manifold which is like carbon fibre in a race series where lots of mechanics might be over the engine bay, then turn this off just in case there was ever any noise on the cam sensor and it was to fire in the intake. We have basically the option of allowing the cam to rotate twice in order to know that the noise was actually not noise and it was the tooth, to know where exactly to fire. The tooth one phase, now we just need to say whether that cam tooth, that single phase, is on the 360, 0 to 360 phase, or the 360 720 phase, the intake or the exhaust stroke. So we basically would assign that. This I know is 0 to 360. And then the disable maximum gap width checking, I really suggest don't turn that off to basically have a good trigger setup and good keying. So once we've got that, we're going to then change this to key by single cam. It's a blue item, so we need to program the ECU. The ECU should now come online, and what we can do is we can crank it over now and see if we get sync. Perfect. So we can see here the sync went to turn, then turn to 360, and then 720. 720 means it's fully in sync, and under starting up here, there is an option here for the valid amount of cam signals to 720 sync and the minimum engine RPM speed. So you can adjust those and you can even make it wait for 720 sync. So when it's seeing the cam sensor and it's all synced up, that it will only start when it's seeing the cam and then fully in 720, i.e. sequential. So what we can do now is we can then obviously go over, as I said before, we can go to our timing mode. Timing mode, set that, say 10 degrees. Timing mode, enable. And then what we can do is we can look at the ignition timing here. When I crank it and it gets sync, you'll see that that will basically not do anything because it's now fixed. And what we can do is get a timing light on the engine and verify that our ignition timing from the ECU, which we have set at 10 degrees, matches what is being sent out. I'll turn that off. Okay, so now what we're going to do is we've got that all synced up with the timing by changing our crank reference. So our crank reference angle, we've checked the timing light in reference to the ECU. They now match up with the crank reference angle. So what we can now do is change the engine enable throttle position back to 125. So when it's less than that, it's active. And then when we go to crank it, so we can see there that it's during cranking, it goes into sync, but it's actually dropping out. And the reason for that is some of these gaps look a bit larger. So because the width of these teeth on the optical sensor are quite large. So a good little test for this, what we're going to do is actually go back and increase these minimum maximum gap widths, put them back at 10. The maximum, put that back at 50. Large gap, because these teeth from the optical sensor are very large. So if you generally find that, you can see the blue item here where it's seeing the short tooth gap. That basically means that the gap widths were too short, it wasn't able to sync off it, and you can see that area in blue here when it did that. And that's a perfect way of doing it, so we can actually see what is going on when that happens and help users. After you've done that, you should see that it fires into life and is happy. Hopefully that allows you to get your engine up and synced.